Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today as it is every day here in my virtual classroom. Step on inside. It's actually well after dark here. It's a good after dark special. In fact, what time is it? 1:45. 1:45 in the morning here. And being the math teacher that I am, let's calculate this thing really fast. I wake up at 3:30 in the morning. Yesterday morning, 5-mile run, taught classes, coached softball, endured the rest of the day. Haven't slept yet. We're an hour 45 away from a 24-hour mark. This is completely stripped down version of someone who dearly needs some sleep, but for some reason can't sleep and is compelled to make the video that he needs to make here as we are working in circles. Not area of circles, not circumference, nothing like that. No. And I'm trying to think what else they've done in circles. Not the unit circle or anything, but just features of circles regarding how chords and radii make central angles, inscribed angles, things like that. Actually, this sheet has nothing to do with central angles. This is all inscribed angles. And I think I'll talk about central angles for a very brief moment in this thing, but I'm going to cover a set of problems here on a worksheet where we just solve this stuff here. So you are going to see if I'm able to make them in some capacity, coming at the end here, a series of videos with circles. I have some old ones that, when I say old ones, I mean like 7 years old or something like that with circles in this nature. So I can maybe go back to those at some point if I need to refer to some other problems again, and maybe even remake the videos that tie in tandem with this new series right here. Okay, enough talk. Let's dive into this sheet and see what the heck this thing looks like here. I'm going to actually rummage through what these problems do look like. The first 4 problems are where I really want to show you what an inscribed angle is and naming them and what has to do with the intercepted arc. And then after that, we actually have to find measures of unknown angles and arcs based on that. There's certain things that features allow us to be able to know exactly what goes where and why. So problems right there every so often. And drawings can get a little confusing look, and I'll tell you what, none of these are actually very confusing looking in comparison to what they could look like. I'd say this looks relatively complex, and that's good that we get one of those, especially because you have me in your corner to help you out with it. But they can get very complex looking. They can have a lot of things fly in the face of exactly what you're doing here. So be prepared to, let's see how I say it. The good thing about watching one of my videos is that I get to actually use, this, I get to overlay this by drawing something like, hey, I get to draw right here and draw right here, and you get to really see the highlight of that. And then I get to erase it. You don't get the same luxury of doing that on your paper if you're doing something like that, but you get that perception. And that's what this thing's going to be all about. Can you perceive what it is that you're looking for well enough? Because I think you're going to understand the math portion of it. The question is getting your brain to understand what it is you're looking at as a drawing. All right, so yeah, this thing is focused on inscribed angles here, not on central angles. But let's go ahead and see what the heck central angles and inscribed angles are both together, one the same, and then we'll be able to answer these 4 pretty easily. Okay, an inscribed angle is some sort of angle that is actually on your circle. When I say on the circle, I mean actually on this rim right here. And you see this is an example actually of an inscribed angle right here. The endpoints of the inscribed angle are also on the circle, so like this one right here. That is an example of what an inscribed angle is. And then a central angle, even though we're not focusing on central angles here, this here is an example of a central angle. It's an angle on the center. You have radii here to build endpoints that are on the circle like that. So the reason why I call these two things out is because there's a specific relationship that these angles have with their respective what are called intercepted arcs. An intercepted arc is a segmented curved portion here on the circle that is captured by your actual angle itself. And I think, look, this one has an intercepted arc right here. It's just not called a central angle or inscribed angle, so there's not much we can say on the measure in its current form. I couldn't tell you very much about this in and of itself, unless I had more information, more data, more things to talk about. But this thing here is called an intercepted arc. I'll just put IA. intercepted arc, and a central angle also has an intercepted arc. And I bring up the central angle only because whatever the central angle's measure is, its intercepted arc is congruent, like that. So these actually have congruent angle measures here. However, whatever the intercepted arc here is for an inscribed angle, the angle measure, the inscribed angle is half of that. So you take this and you divide it by 2, or if you want to find the intercepted arc from the angle, you go ahead and you double that angle measure. So I'm not going to sit around and do the proof portion of this, but that's what those things do. Now, I don't believe we're going to actually run into central angles and do things with them, although I will, call attention to them if they do. We might have straight angles because we might have diameters, so I'm going to have to run into those for sure. So that's what those things are in a nutshell, pretty quickly there. And some other important things of note, a circle's full measure is 360 degrees. We are going to be naming things with certain conventions. You might know how to name angles using 3 letters, which is exactly what we're going to do, and how to name intercepted arcs. I'm going to get in that right now. So state if each is an inscribed angle. We start with number 1. Yes, it is the angle that you're referring to there. We can call it angle, say, BAC or angle CAB, either or. The endpoints should be on the arcs right there when you name them. And the intercepted arc is, once again, the arc that's captured right here. Notice the endpoints are B to C. So this is the angle. The intercepted arc is BC with this arc symbol above it like that. As opposed to doing an actual segment bar, it's a segment arc like that. Number 2 is a no. It is not an inscribed angle. The angle is not on the circle, despite the fact that it does have 2 endpoints that are on the circle. And that's just to mention, although LM may be the intercepted arc of whatever this angle measure would be, it's not half of it or equal to it. I can't determine it or calculate it like that, right? I don't have a mathematical way of going about that. Number 3 is an inscribed angle. This is an example of having a diameter. When you see that center and your chord goes through the center right there, then it is a diameter. That doesn't change the fact this is an inscribed angle. It is. I just wanted to call attention to that. And there's something we're going to be able to say about that in a lot of problems there, because we're going to have what's called a semicircle, something like that. Now, this is the inscribed angle VXW, angle VXW. Its intercepted arc is the arc portion captured by the 2 endpoints of the inscribed angle, which is VW, like that. And then number 4, although it is not an inscribed angle, it is a central angle. So one more time, those will be very relevant and important when it comes to future calculations. It's just for the sake of this thing, it's not an inscribed. So, you're not going to take half the measure. You want to make sure to know to identify those. All right, here we go. Find the measure of the arc or angle indicated. We're referring to this question mark right here. We need to find out what this is. Now, in order to do this, what you have to do is, understand what kind of angle or information you have here and, how you can use it mathematically. So right now you have what's called this 80-degree arc measure. The measure of arc BC here is 80 degrees. It's 80 out of the whole 360 right here. To find out this angle measure right here, it will be half that of the 80 degrees. Measure of angle BAC is 1/2 that of the measure of arc BC. And don't worry, I'm not going to be writing this every single time. This is kind of getting you that idea of what's happening here. Half of 80 degrees is dividing 80 degrees by 2, and you get 40 degrees there. 40 degrees. That's what that measures in, as it is an inscribed angle. Okay, number 6. Now, this one right here, there's a lot of information I could actually pull out of this one, and I almost feel inclined to bring it all up. But for the sake of the problem itself, there's really only one thing that I care about, which is given this inscribed angle right here. And it's this is one of those examples where it's going to be harder to tell that you have an inscribed angle. But I have an inscribed angle right here. If you see what I'm going to draw in green, notice what in green is. That is an inscribed angle with this intercepted arc right here. It doesn't matter that what you have is the appearance of a triangle. This line, not a line, a chord. This segment right here, if I hide it, is this not an inscribed angle that you see right there? It absolutely is. Look at this other one. So adding lines to this thing does not change what is already there in the first place. If I add this line back and add this line and add this line and add this line and add this line and add this, that's still an inscribed angle right there. You know what I mean? Adding more things doesn't take away from that. Your goal is to determine what it is you're looking at. And you might wonder how to do that. It's really simple. Follow the lines. Find out. And not everything is inscribed angle based. And, everything's going to get a little harder when you see more diagrams. But I have an angle on the line, on the circle, excuse me. And then if you follow it to another endpoint there, no matter what's there, if you follow it to endpoints, then you have what's called an inscribed angle. Period. If you can determine its intercepted arc based off that, even better. So that's what we're going to do right now. The intercepted arc WV, the measure of arc WV, is going to be double that of the measure of the inscribed angle here, WXV, right? 2 times that measure. Let's put in parentheses. And the measure of angle WXV is 42 degrees. So the measure of arc WV, we are going to take 42 and double it, and we get 84 degrees right there. So that's how much this is right here, being double that of its inscribed angle. And remember, if we had a central angle, actually, let me bring this about right now. If I had a central angle here, and if this had a point, let's call it T, measure of angle WTV would be exactly 84 degrees right there, because its intercepted arc is equal to its measure. So central angles are equal to their intercepted arc. Inscribed angles are equal to half of that. Okay, number 7. And by the way, I was going to mention that I'll probably go back to this drawing based on showing you. I'll show you later how I know that this is a right angle, maybe, if I run into something of that nature when I have to use it. Number 7. We have to find this arc right here. Now, this is one of those instances where you got to kind of work around your diagram a little, see what you can pull out of here when you can, where you can. For example, they show 35 degrees, and where are they bringing that up? I can only imagine it's this right here. By the way, I haven't done this assignment right now, so what you're going to see me do is just strategize and talk to you about what it is that I see and how it is I can use the information that I have. So I have 35 degrees right here, which is an inscribed angle with this intercepted arc, FP. By the way, when we name arcs, you might have noticed that so far I've been using 2-letter name designations. That is used for what are called minor arcs. A minor arc is an arc that's less than 180 degrees. But if I wanted to somehow figure out from F to P this way, this would be considered a major arc, and I would name it differently. I would actually use 3 letters. Maybe use F, E, P, or F, D, P. You'd use 3 letters if you're referring to a major arc, or something called a semicircle, which is what we're actually probably going to be using for this problem when I look at the question mark here. Anyway, the measure of arc FP should be double that of the 35 right here, and that's going to be 70 degrees. This is an example of me showing less work because I have a lot more to piece together. It's like, where does the 70 come from? Let's go ahead and label and put it in. Now, they're asking about the question mark here, and I'll, there are 2 different ways we could go about the problem based on whether you want to talk about, once again, I actually do have another right angle here, maybe talk about why in a sec, but it actually has to do with the fact that this whole thing right here is actually a semicircle from F to D, from F through P to D. The measure of arc FPD, and semicircles should use 3 letters as well, is 180 degrees. So that's 180 degrees right there, and we know that this is 70 degrees right here. So we have to find the measure of arc PD right here, measure of arc PD, by taking a pretty basic notion, and I'm sure you would not only agree with it, but I'm sure you're also coming to understanding it if this is your first time learning this, that if I add this 70 degree arc measure and this unknown arc measure right here, I should be getting 180. So 70 plus the measure of arc PD is 180 degrees. And so if I subtract 70 from both sides, the measure of arc PD is 180 minus 70, which is 110 degrees. And that is the answer. Now, although I still haven't brought up, and I think it's worth just bringing up now. Let's erase a lot of the stuff here. Although I haven't yet brought up why that thing's a right angle, which I'll talk about now, it does have to do with that semicircle approach right there. So if you have a diameter, specifically a chord going through your center, if you have a diameter right here, then its endpoint's intercepted arc is that of a semicircle. It is 180 degrees. That means its inscribed angle right here being half of that would be 90 degrees. That is 180 over 2. So you take the semicircle, 180 over 2. So you do have right angles there that are implied. They tend to not tell you because that's something you'd be looking up. And I bring that up because we have this scenario right here. We have a diameter right here. Therefore, this inscribed angle FED is half that semicircle right there, which is 90 degrees. And I guess that's me working, I guess that's kind of like I'm using the information to explain why it's 90 to get back to the fact that it's a semicircle. So I guess this wasn't of huge use. I was going to say take 90 and double it, and you get the whole thing as 180. But that's the whole reason that's 90 in the first place. So I guess I don't know. I'm bringing it up now just so you have it. What can I say? I've been awake for 23 hours. All right. Number 8. Number 8, we're trying to find this guy right here. I'm already seeing 2 different ways I can go about it, and we might as well do both here. One is actually using the notion that you do have a triangle inscribed in this circle right here, and all triangles have an interior angle sum of 180 degrees. So if I take the 49, the 70, and this unknown measure of angle DBC right here, I add those together, that should be 180 in and of itself. DBC equals 180. And I bring that up because DBC is an inscribed angle for this intercepted arc. So if I find out what DBC is right here, I will double it and I will get the intercepted arc measure here. So 49 plus 70 is 119. And if I subtract 180 from both sides, I'll get measure of angle DBC as 61 degrees right there. So this is 61 degrees right here. So the measure of arc DC is going to be double that of 61. I should have put 2 times 61, that's okay. And that is 122 degrees right there. So that's what this is here, 122. And I would be done. I would be done. I will, however, show you an alternate version of this, and it's by circumnavigating this entire circle. We do alternatively have 2 other inscribed angles, such as this one right here, angle DCB. This 70 degrees doubled would give me the intercepted minor arc DB right here, which would be 140 degrees. Now, if we look at the next intercepted arc right here, BDC, as that's 49 degrees right there, we double that one to get this intercepted arc right here from B to C, and that would be 98 degrees. And then this last one right here, the measure of that arc, what we can do is we can say, well, all 3 of these arcs combined should add up to 360 degrees. Boom, 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 like that. So that means if we do 140 plus 98 plus measure of arc DC, we should get 360 degrees, right? And that's, quite interesting to look at when we talk about the triangle's angles add to 180 and the arc's measures add to 360. Well, yeah, that makes sense. The inscribed angles are half that of their intercepted arcs. So this adds up to half of what the arcs add up to. 140 plus 98 is 238. And if you subtract 238 from both sides, you'll get measure of arc DC equals, looks like 122. And that is the same exact thing as we got right there. So you see 2 different approaches there. And listen, these problems, one of the reasons why I sometimes have trouble talking about these things is there are so many different ways to do the same problem. Some are faster than others, some are better than others, some are flying more in your face. But as I haven't done these problems before yet, I'm just navigating with what it is that I can, play with in any such way. And these are not the complicated versions of problems. These are more the easier ones, in fact. Okay, Not like easier as in like, oh man, why aren't you doing the harder ones? It's just that they can get more difficult depending on what you want to do with it. Okay, number 9 right here. We have to find out this arc measure right here. And these are the bits of information that we have. Boom, 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 boom. This is a quadrilateral, and I'm going to not talk about quadrilateral properties at this very moment in time, although I could to bring up what it is we want to do here. But the basic premise for me as I'm looking at this and strategizing, more than one way to solve this, is that to find this right here, this is a portion of larger arcs, such as this one right here. So it's like, okay, if I could only find out what this is right here, then I could take that away from, something. So there are a lot of things I can do to navigate this thing. Sometimes it's just about writing information down. But I need to come up with this. The problem with finding this is it is not the intercepted arc of an inscribed angle or a central angle or anything. Like if these two, if there was an inscribed angle right there, I would just double it. So we have to kind of work around this a little bit. What I'm going to do is help you pull out some information and see what we can do with that information after. Now, this 119 degree measure is an inscribed angle, boom, with this intercepted arc, boom, right here, this major intercepted arc like that. 119 doubled is 238 degrees. So this whole thing right here is 238 degrees because we doubled the 119. So measure of arc FGH, as it's a major arc, is 238 degrees. Now, why does that possibly help you? Because this part's 168 plus something is 238 right there, right? Both of those together would add to 238. Doing kind of the simple math there, 168 plus 70 is 238. So this FG arc is 70 degrees right there. And that's good because that means if I could find out maybe what this whole arc is right here, I could take 70 away from there and then I would get our answer. Well, 65 degrees is this inscribed angle right there for this intercepted arc. So if I doubled the 65 degrees there for measure of arc VG, we will get, whoops, not segment. I'm doing a lot of segments for my integrated math 1 classes, so we're doing triangle congruence proofs right now. That's going to be 65 doubled, which is 130 degrees. So this whole thing is 130. Whole thing is 130, and 70 degrees is one portion of it, and this measure of the arc is the other. So measure of arc FV is 130 degrees minus 70 degrees, which is 60 degrees right there. So this guy is 60 degrees right there, and boom, we're done. Now there are other ways, again, that you could come up with this here. This is plenty. I do want to talk about quadrilaterals if I have to in the future. The thing I will bring up that would be of most importance to you, well, 2 things in quadrilaterals. Number 1, their angle measures add to 360 degrees. This plus this plus this plus this is 360 degrees. Not just for inscribed quadrilaterals, for any quadrilaterals. But number 2, for inscribed quadrilaterals, quadrilaterals whose angles are inscribed inside of a circle like this, opposite angles are supplementary, which means if this is 119 degrees, the angle opposite is 61 degrees. They add to 180. If this is 65 degrees right here, this is 115 degrees right here. And, you can check and see if those add to 360. They should, because these add to 180 and these add to 180. But that's true for inscribed ones. And, there's probably a way that we could have used that information to get the answer to this problem here. Whatever. All right, number 10, and I'm already seeing what I want to do with this one personally. I take this 95 inscribed angle and I double it to get the measure of this arc right here. Can't tell if it's a minor or major arc, but I don't have another letter to identify the fact that I want to talk about this RQ. 95 doubled is 190 degrees. Now, in total, the 75 plus the 190 plus our unknown should be 360 degrees. So if I take the measure of arc SQ that I'm trying to find there, I will go ahead and take 360 degrees and subtract the sum of 75 and 190 like this, which will be 360 minus 265, which is 95 degrees. And that's it for that one. That actually seemed easier than, say, this one, number 9. Yeah, with these quadrilaterals here, I can't guarantee that there's actual use. Oh, I actually do see some use of this one right here now. Solve for x. Now, once again, there's more than one way to do the problem. I'm going to use the quadrilateral property first that I just brought up, and that'll give you an alternative if you want to check it out. All right, number 11 here. We have 50, we have 30x. We have to solve for x this time. And so maybe just write a bigger equation out of what we have. And we have this 110-degree angle measure inside of an inscribed quadrilateral. Now, I just brought this up previously. A quadrilateral inscribed inside of a circle has opposite angles supplementary. If this is 110 degrees, this one here is 70 degrees. These two would have to add to 180. Now, I bring that up because 70 is the inscribed angle with this intercepted arc, the one that uses 50 and 30x. So we know that 70 should be half that of these two, or better yet, these two to combine, or double that. And I say just better yet because sometimes we don't like working with fractions if we don't have to. If we take double that of 70, then it'll be equal to its intercepted arc 50 plus 30x. There's a good equation that we can use to solve. So again, the 70 came from being supplementary to the 110 because the inscribed quadrilateral property, and then I can use that to solve. So I'm going to do this way first. I'll give you an alternative in case you didn't see or know that. Subtract 50 from both sides and divide both sides by 30. We get x equals 3. So there's one version of the problem like that. Maybe my go-to. But that's something you'd have to know as a property. The second go-to would be taking 110 there as the actual inscribed angle for this major arc, this intercepted arc here, KRQ. And the measure of arc KRQ right here is double that of 110, which is 220 degrees. So right here, these three arcs, 50, 30x, and 220, add to 360 degrees. And that's probably, honestly, where a lot of students might see that first. They're probably not looking for that opportunity there. It depends on what's set up for your problems. So anyway, those add to 360. You get 270 plus 30x is 360. Subtract 270 from both sides. You get right back to here. 30x is 90 and x is 3. Okay, so those are two different ways to go about that problem there. Okay, solving for x here, straight up, inscribed angle. And the inscribed angle is half that of the intercepted arc 192, or 192 is double that of 31x plus 3. So if I double my 31x plus 3, I am getting 192. Okay, that's the idea, that's the setup. Let's distribute, well, let's divide both sides by 2. I'd rather do that instead of distribute. We should have taken half of 192 to start. 31x plus 3 is 96. Subtract 3. And divide by 31. We get x equals 3. How boring. We get x equals 3 again. And that's the solution. All right, 4 more problems here. So solving a system of equations where I have to, that's going to be less about the geometry and more about the algebra once we get things set up, but it's still strategy based. All right, find the measure of angle NLM. So we want to find out what this thing is right here. Now, in order to do this, we'll have to first probably solve for x. So LNM is the inscribed angle with this intercepted arc right here, 7x minus 10. If we find out what x is, we can substitute it into here, take half of it, and we will get the angle. We got to find x first. Now, in order to find x, there's this idea of this diameter right here, which makes this the semicircle LMN exactly that. It's a semicircle. These add to 180 degrees total, this arc and this arc right here, or the whole semicircle. So if I take 13x minus 10 and add it with 7x minus 10, I will get 180 out from it because of the semicircle nature. 13x plus 7x is 20x. Negative 10 minus 10 is negative 20. And we will add 20 to both sides and then divide both sides by 20. We are getting x equals 10. So I'm going to take that 10 and shove it up my x right here. 7 times 10 minus 10 is 70 minus 10, which is 60. So this is a 60-degree intercepted arc, and this inscribed angle should be half of the 60. So this is going to be 30 degrees right here. So measure of angle NLM is 30 degrees. Okay. All right, so there's the work on that one there. Okay, find the measure of arc FGH, and we have the information for this inscribed angle and the inscribed angle opposite. Now although I just explained before that opposite angles in an inscribed quadrilateral are supplementary, let's say that's a property or theorem that you did not know when it came to solving. Is it impossible for you to solve? No, you just have to kind of do some workarounds to figure this thing out, and I'll show you exactly how this is supplementary by doing the practical version first. If you consider, the whole idea about inscribed quadrilaterals is that their intercepted arcs complete the circle. When you look at this inscribed angle right here, FAH, right there, its intercepted arc is this major arc here, FGH. Notice that in purple. And then here in green, if I take the inscribed angle FGH, its intercepted arc is FH right here. So just look around the outside of the circle and see that nothing is uncovered and nothing contains overlap. That means together, these and these add up to 360. And their actual measures would be taking the 38x plus 5 and doubling it to get its intercepted arc right here, plus taking the 21x minus 2 and doubling that one for the green's intercepted arc. And again, together, those would add up to 360. Now, before I distribute, I'll do kind of what I did from this previous problem right here. Instead of distributing, divide everything by 2. And what happens is you divide these quantities by 2, over 2, over 2, over 2. And notice what actually comes out here. What comes out is 38x plus 5 plus 21x minus 2 equals 180. You're getting, once again, another look at the fact that these two add to 180, therefore they are supplementary. And that's no coincidence. That's no coincidence that that's true in this case. They should be supplementary. They should add to 180. So that's something I could have started off with, and I would have. But for those who didn't know that, or for those who don't know why, or for those who need a practical approach and, they're not aware of what to do, you have other alternatives. And you could have distributed the two. But I want to show why those actually, or that they add to 180. Okay, I'm going to go ahead and solve the rest of the way now. 38x plus 21x is 59x. 5 plus negative 2. 5 minus 2 is 3. I will... Oh, I thought this was going to equal... 3 again. Oh, actually, no, it does. It does. 59x equals 177. Divided by 59, we get x equals 3. Give me something else. I guess we got 10 this one time. Oh, and I'm probably not done. We have to find the measure of an arc. Find the measure of arc FGH. Okay. Measure of arc FGH. Measure of arc FGH. Let's go ahead and erase some of this stuff. It was the purple. It was the purple one here. FGH is that major arc there that should be double that of its inscribed angle 38x plus 5. So I'm going to take double that of 38 times 3 plus 5. Remember, we got x equals 3 here that we're substituting that into. So 38, let's double. 38 times 3, 114. Hold on. 98, yeah, I think it's 114 plus 5 is 119. And double 119 is 238 degrees. It's possible I might mess up a math thing here and there. Yeah, you can't blame me. About an hour removed from being a 24-hour thing. But I believe that's correct. I don't know. Okay, 2 more problems here. Last 2 for inscribed angles. And like I said, this is not the most complex set of drawings right here, but promise this one for my kiddos. All right, number 15. Number 16. We're solving for both x and y. Now, again, more than one way to solve these problems here, but the basic crux of it, no matter what you do, is you got to build a system of equations here. You have to build at least 2 equations with this to solve for x and y. And I'll be honest, I'm not going to spend a long time talking about and explaining how to solve the system algebraically. I will do it. But this teaching right here is in the how do you set things up geometrically regarding the inscribed angle thing. The rest is, need to know, but it should have been known. If you're graduating to this stuff right here, it's that you've done systems of equations before. So there are a couple ways we can, there are a couple equations you can set up, but as long as you set up two true equations that are uniquely different from one another, that, then you can solve for your two variables. So one of the ones that we can do right here is we can say that these two opposite angles add to 180. And we can do one that says that these two opposite angles add to 180. I think that's a fair one to do. An alternative is maybe do one of the two sets that add to 180 and do another one that says all four of them add to 360. But what's going to happen is you're going to take out information with these two that add up with those two that add to 360, and you'll take out the excess 180. Point is, we should probably just combine them in such a way that we do this plus this is 180, and then this plus this is 180. If anything else, you're working out that property. But yes, this is the one that doesn't have any excess information in it. Okay, so what I'm going to do is I'm going to combine like terms. In a system of equations such as this one, I can solve using certain methods like the elimination method. And that's probably what I plan on doing right here. So sorry if you don't really know what it is. But taking this equation here, 10x, there's nothing to combine here. But what there is here to do is subtract 6 to the other side of the equation. And I get 174. And you might see me reduce that in a bit because they're all even numbers. And then right here, same thing, all even numbers. I can combine some things, and I'll get 4 minus 6 is negative 2. So I have 18y plus 10x minus 2 equals 180. If I add 2 to both sides over here, I'll get 182. And if I rewrite this thing with the x term first, I'll get 10x right there. So 10x plus 18y equals 182. And here's what we have is called a system of equations. It's two different bits of information in the same diagram to help solve for x and y. And I said I was going to reduce values. I could, but right now I'm flying in the face of having a 10x and a 10x right here. And if I line these things up and add or subtract or do whatever here, I can eliminate the x's to solve for y. If I multiply the whole bottom equation, say by negative 1 like this, boom, 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 change all the signs to negatives, then I'll have 10x minus 10x to get 0, and those variables are eliminated. 16y minus 18y is negative 2y, and 174 minus 82 is negative 8. Divide negative 2 from both sides, you'll get y equals 4, positive 4. And that's solving for y right there using what's called the elimination method. Now I can take the y and substitute it into any of these things here to find x, any of the equations, or perhaps even an expression or so if I had some measures involved with it. Let's just get the idea of the supplementary one, say in blue right here. 10x plus 16y plus 6 is 180, or what was the one I rewrote right here? Right here. So 10x plus 16 times 4 is 174. So 10x plus 64 is 174. If we subtract 64 from both sides, 10x is 110, and divide both sides by 10, you get x equals 11. So solve for x and y. I'm used to writing a system of equations as an ordered pair, like 11, 4. I don't think that's necessary for this problem. But solving for x and y right there. Okay, you may or may not notice, as I was recording, my hard drive actually just ran out of memory. It just ran out of space. Storage right there. So sorry if there's a hitch right here. I just deleted some old videos and brought it back. But the last one right here, number 16. We have these two. I mean, it's the same thing as what we just did before for the most part. I can't think of what else I want to do in the problem. These two add to 180. These two add to 180. And we can set up a system of equations right there. These quadrilaterals. And, as I was clearing that stuff up, I was just going back and thinking about the fact that these are definitely not the hardest of problems that we'll run into when it comes to the discerning of circle stuff. In fact, my students have already worked with harder problems. Ones where they had to navigate a little bit more around the problems. They came in parts, though. It was like they asked you to solve certain parts, And then I think one would help you lead to the other strategically. So if they asked you to find that last part only without the parts leading up to it, I think those would actually be a little bit harder. And yeah, I'll definitely have to do some more problems regarding inscribed angles. And I want to do some regarding central angles as well. I want them all together, and you can definitely come across what confusion there may end up being in problems. All right. If I add the 1 and 74, I get 75 there. So 7x plus 2y plus 75 equals 180. And then if I subtract the 75 over, I will get 7x plus 2y equals 105 right there. That's one equation in my system. The other equation in my system right here, if I do 100 minus 10, I get 90. I'm going to put the 6x first here. 6x plus 2y plus 90 equals 180. Yeah, it looks like they're going to be fair with you guys here. If I subtract 90 from both sides, I get 6x plus 2y equals 90. Anyway, I was saying they're being very fair for you guys here with this kind of problem setup, saying, we'll make the system easy for you. We'll just let you subtract away 7x minus 6x, 2y minus 2y, 105 minus 90, and you'll eliminate y's immediately. Sometimes in systems of equations, you got to do a lot of work to get yourself additive inverses such as these to cancel them out. 7x minus 6x is x, 105 minus 90 is 15, and that's what x equals. For y, you're going to have to take the x, substitute it into one of the equations that you've had from before to solve. So I'm going to take one that's as simplified as possible, either this original or this one here before we made it negative. So let's take that equation here and do 6 times 15 plus 2y equals 90. That'll give you 6 times 15 is 90, right? So that'll be 90 plus 2y equals 90. Subtract 90 from both sides, you get 2y equals 0. Divided by 2, you get y equals 0. You get y equals 0. So does y equals 0 actually work on that when x equals 15? I'll just double check this one and see if it does work. So if you set y equal to 0, this easily just becomes 0, or this becomes 100 degrees right there, and this becomes 74 degrees right there. Let's see what happens when x is 15 right here. 7 times 15 is 105, plus 1 is 106, like that. And then 6 times 15 is 90, minus 10 is 80. So do these work out? In a couple ways. Number one, are they supplementary? Number two, do they add to 360? I guess if they're supplementary, they do add to 360 because 180 plus 180. So 106 plus 74 is 180. 100 plus 80 is 180. So this 180 plus this 180 is 360. Seems to work out. Seems that y was just a little decoy 0 right there. And that is it. Okay, and that is it for this one here. And I definitely want to find a series. I'll find some of my old problems at some point perhaps and make a video out of those, or as we do future examples on these, you get to see the more complicated stuff where it gets to let me think a little bit more strategically and how to go about solving the problem too, just to talk through it better, because inscribed angle drawings can be really confusing. That'll do it for me, guys. This is Mr. Robinson. Thank you so much for watching. 23 hours. It's 2:30 in the morning right now. 23 hours of being wide awake. Thank you so much for watching. Take care.